So today we're going to do the last part of magnetostatics. There are a couple of loose ends that we need to talk about. The first is that we saw the magnetic scalar potential at work at the end of last class, and we used that to come to Ampere's law. But we only formulated Ampere's law in integral form, and we still need to convert that to differential form. So we'll have to do that. We've used Ampere's law in a couple of cases, and I made a note in passing on how you could use that same magnetic scalar potential, but then work in the domain of the magnetic field instead of the potential to come to a different formulation of how the magnetic field depends on current, and that is the Biot-Savart law, but we didn't actually take Biot-Savart for a test drive. So we'll do that today as well. And then the magnetic scalar potential, we will try to avoid talking about it because it's a useful construct, but it's not a very common thing to talk about. But we do need to talk about the magnetic vector potential, and we have discussed this general principle of fields that you can always decompose it in terms of a rotation and a divergent component, or do a curl and divergence decomposition, or do a Helmholtz decomposition. Those are all the same thing. So so we've used the scalar potential, and we're going to ignore that for now, and then we'll do the vector potential. So we'll need a curl of that vector potential to get to the magnetic field, and we'll take that for a test drive too. And then we'll see that just like with the scalar electric potential, there is a certain amount of freedom in choosing offsets or references. For the electrostatic scalar potential, that's very straightforward, because you have, your electric potential is just a line integral through the E field, and you can choose to start that line integral anywhere, and that is known as choosing a gauge. And the fact that you can pick it anywhere, that means that you have gauge freedom. So there's a similar thing that you can do in magnetostatics, and that has to do with what you can do to the vector potential. So you have a certain amount of freedom, and we'll quantify what that means, and then we will also describe what it means to fix that degree of freedom. Now, they're not independent, so we can't describe yet how they are related, because we haven't really completed all of Maxwell's equations. Notably, we haven't done Faraday's law in proper form, because we've done everything statically. So we haven't done any DDT. We also don't have an Ampere-Maxwell equation. We just have Ampere. So we can't really discuss yet what that gauge freedom for the electric potential and the gauge freedom for the vector potential, the electric potential and the magnetic vector potential, how they're related, because they are related. But together, if you transform one and then you make some other kind of similar transform to the other, and they're somehow related, then you have some kind of a freedom. So that gauge freedom we will only talk about today in terms of the magnetic vector potential, but we will not yet connect that to how that is related to the associated changes that you need to make to the electric scalar potential. So we talked about Ampere's law, right? We had it formulated in integral form. So we had this integral of B dl, and that was 4 pi over c, and then integrated. Actually, we had it like this. I. And this I sometimes would be called the I enclosed, and we call that I enclosed because actually what we're talking about is an integral of current density over surface area. Okay, so now what we mean, well, we are talking about some kind of a current. That's our current. And then we can take a line integral in this direction. And oops, that is our integral of b dl. So we're taking that integral in this direction. Of course, I'm doing this wrong way. Hang on. Yes. Nope. Yes. It's harder to do it like this. And then, of course, the current goes here. No. See, I'm already running into issues. Here we go. Okay, so that's our current. Now, what do we mean by that conversion from I enclosed to J? So then instead, what we're doing is we're saying, okay, so there's this this surface here that is spanned by that contour integral, and that surface, we're going to call that A. So then that is the surface that you're integrating over here, but that is actually the surface that is circumscribed by this line integral. So this is over the edge of A, so that's how these two are related. Okay, so so then J here is now current density. The rest is the same. Oops. Yes. Now we can rewrite our BDL a little bit. So we can actually write it as a hang on. Oh, not a surface integral. So we can write it using Stokes. So these two are the same. And now we have a hang on a second, what am I doing? So we can rewrite this as a surface integral of the curl of B over that same surface area. Now you see that we have on both sides a surface integral, and this is not a contour integral, this is a surface integral of J ds. And we did not specify at any point that that this thing needs to have any particular shape. As long as it is a surface with a well-defined edge, we can say this is this must hold. So therefore, this must hold for all. So this must hold for all Ampérian surfaces. So Ampérian surfaces are flat surfaces; they don't have an inside. In contrast to Gaussian surfaces. So therefore, we can write it in differential form is 4 pi over C J. Okay, and this is, of course, Ampere's law in differential form. Okay. Okay. So now that we have that, we can look at the other the other aspect of how to find magnetic fields. So let's remember that, actually, let me start a new one. So let's remember Biot-Savart's law. Which states that we can calculate our B field as 1 over C. And now this is a contour integral of IDL crossed with R hat over R squared. So using that, we can find the magnetic field for any kind of current, right? So if this is our current, so I'm gonna draw a, hang on a second, draw a coordinate system. So that's our coordinate system, and then this is our current. It's a current carrying wire. It's a nice little loop. It's got big radius R, big R. And now we have a current that flows in this direction. And now we can ask ourselves in this point, oops. What is B? So let's work on that for a minute. Let me put a thing in. Nearpod. So in this case, so there are a couple of tricky things about this setup. The first is what I have now colored green here. That is the relation between that DL vector and that R vector. Now R is the position vector that points from the section of the wire that you're integrating over to the point of interest. And we want to know the field in the middle here in the origin, and that's where B is, right? That's why there's a red arrow. So that R vector is actually pointing inward. That's going to turn out to be important in a little bit. Now, this one is actually quite straightforward because that R and that DL are actually perpendicular to each other, almost by definition, because actually, in this case, the green R vector is actually the negative, the position vector for points on the circle. And for a circle, the position vector and the tangent are perpendicular to each other. So this cross product of DL cross R is always going to be DL times R, and R hat has a length of 1. So this integral becomes a almost the world's simplest integral. So we have a 1 over C, and we still have this one. Now we have I, and now we're integrating over theta, obviously, and we need R d theta. But actually, let me actually change that to big R because that is important. And then over R squared because it's going to be on the circle. Okay. Now none of these things actually depend on theta, so we just pick up a 2 pi. So we get 2 pi I over C times R. And then the direction, in this case, the direction is positive, in the positive Z direction, which you can verify with the right-hand rule, but you can also find with our from our cross product. Okay, so let's see what happens if we pick a point that is actually not in the center, but it is here. In that case, the setup is a little bit different. So I'll draw the thing again. We have our circle. We still have our current that's circulating in this way. And now we want to know the field here. And we need to consider this cross product of this with this vector. And we also need to consider symmetry. So if you take Biot-Savart's law, so you have that B 1 over C I dl cross R hat over R squared. R squared. Then that dl crossed with R is going to give you a contribution dB. So let me draw that here. So there's going to be contribution here that we're going to call dB vector. That dB vector is actually pointing in this direction. It is not pointing straight up. So that's our dB. But of course, symmetry dictates that because we're integrating over a circle, for every point here, there's going to be a point on the opposite side that has the exact same magnitude of dB, but it's pointing in the opposite direction. So when we integrate over the circle, there's going to be, so that's a dl prime. When we integrate over the circle, there's going to be only the z component left. And now it's not too hard to show that that z component, that's just straight up geometry, that dB z component is actually dB times the sine of phi, where phi is this angle. Okay, now if that's that angle, then that is dB times big R over little r. Okay, so now if you integrate that, you want to integrate and only get the z component, you get 1 over c, and you get an I r d theta, and there's a r squared here. With an extra, with an extra r thrown in on in front, because we only need the z component. Hang on a second. I am gotta throw out these two things. Yes. So we get r over cr. Okay. And then we're still integrating over theta. So we get a 2 pi big R squared times I over CR cubed. All right, let me make sure that I got my math right. Yes. Okay, and R now is, you can describe as function of z by just plugging in the Z dependence. And now you get R squared plus the Z coordinate squared 3/2. All right, and this is still, of course, in the Z direction. So finally, B is B Z Z hat. So in the for Helmholtz coils, we usually set these up a little bit differently. We set up the Z-axis in this direction. So that means that we're setting up 2 coils, and they both have a radius R, and they have a current that flows. Current that flows in the same direction. There is also a case where you wire them up in the other direction, and then the idea is to set up this system in such a way to choose this distance, let's call that distance A, in such a way that if you find the field here, be close to uniform. So what do I mean by that? Well, if you look at this expression, you see that in the limit of Z going to infinity, obviously this field vanishes. But if Z is 0, it has that finite value of the field that we had calculated before. So the B field as a function of Z for the first coil goes like this. And the B field for the second coil goes like this. So let me make sure that I color code this properly. So this is the second coil. And oops, redo that. Nope. And then this is the first coil. So what do I mean by uniform? Well, if you do this on the end here and you find the net field, then here, if you let the fields overlap, it's not going to be very uniform because it's already tapering off and it's tapering off here. So the net field will actually have a dip in the middle. If you put them too close, then it's also not going to work. So you get the highest uniformity if you make sure that this point of inflection, which is right here, and this point of inflection, which is right here, is exactly equal. And that is the case when A is R. And that is what the usual Helmholtz coil setup dictates. And you can find that point of inflection by just finding this, taking the derivative of that expression with respect to Z, setting it to 0. So if the coils are far away, then the net field looks like this. So then you just have a field. Nope. So you get a field. No, come on, Henk. That's really sloppy. You get something like that. That's when they're far away, all right? And then when they're too close, you get this. So when it's just right, you get something like this. So somewhere in the middle. So it would not be, you would not call that a stable equilibrium, right? You would call the blue one stable because it's sort of a well, even though that's not really, it's not really a well because it doesn't translate directly to potential. But if you want to think about it that way, then the blue one would be the stable one, if you want to think about it that way. But the red one, you know, the B field is horizontal there, so it's stable, but it's metastable if you want to think about it that way. so let's go back to, so remember that the Helmholtz decomposition where we could say that the B field, or any kind of vector field, is uniquely specified by the gradient of some potential plus the curl of some other vector field. So this is phi is then a scalar field. So that's a scalar field. And oops, and it's our vector field. So without loss of generality, except we're ignoring the scalar field, like I mentioned in the introduction, we can just say we should be able to reformulate our laws that are talking about magnetism and how currents generate magnetic fields. We should be able to translate that straight into the vector potential. So the vector potential which is A, and it's at this point it is implicitly defined as that thing that when you take the curl, you get B. Then the question is, okay, well, how do you get that vector potential, and afterwards, what can you do with it? So let's remember that from Biot-Savart, we had our B is 1 over C line integral IDL R squared. Now I'm gonna write it like this, and we know that we can write this as follows. So we can use the fact that the gradient of 1 over R, this is becoming infinitesimally small, hang on a second, that the gradient of 1 over R is minus R vector over R cubed. So if we stick this in here, that's squiggly, then we can rewrite this as the line integral of IDL vector crossed with the gradient of 1 over R, but we need a minus sign, so we got to take a minus sign here. And now, if instead of using a current carrying wire, we just use a current carrying medium, so we're going to generalize to a current, carrying medium. We can, instead of doing this as an integral of IDL, we can make it a volume integral. So then B becomes minus 1 over C. And now this is no longer contour integral. We just get a J and a D, crossed with the gradient of 1 over R still. Hang on a second. Dropped one term. Hang on a second. I think I dropped a term, but I'll get to that in a second. But I want to finish my thought first. Then we're actually allowed to take the Nabla operator out, because if you work this out, the curl of J is 0, so that means we can pull this out, and then we get 1 over C, and this is a D3x prime, and now we have the curl of J over, and again, I'm missing a term here. I will fix that in a little bit. And because I swapped the Nabla operator, and the J, then that means that I can drop my minus sign, and then I can pull it out of the integral, because I'm allowed to do that, because the curl of J is 0. So then we get curl of 1 over C, and then we have the volume integral of J over R minus R prime D3x prime. I'm going to clean up a little bit my phantom presses. And then, because this is supposed to be equal to the curl of A, this thing is A. So finally, we got 1 over C, the volume integral, J D3x prime. Now compare this with the scalar potential from electrostatics, which is just rho D3x prime over R minus R prime. So I hope you realize that this scalar potential and the vector potential formulation look very similar. There's a source term, and then it goes like 1 over R minus R prime, which is measuring the distance to that point of interest. 3, measuring the distance to that point of interest, and then they look the same. Now, it's not a coincidence that they look the same, because actually it turns out that the scalar electric potential and the magnetic vector potential together form generalized what they call a 4 potential. And when we get to relativistic description of E and M, we will see how that works. Okay, so let's talk gauge invariance. Let's say that we have a vector potential, a red vector potential A here, that gives a field B, and that's our red field B. And we take another vector potential A, but we're calling it A prime, and you take the curl of that, you get B. Is there a are we allowed to change A to A prime without affecting B? And the answer is yes. So for instance, what we can do is we can say, okay, I'm going to take my my green A prime, and I'm going to call that our red A, but I'm going to add the gradient of some kind of a scalar field. So the question is, are we allowed to do that? And the answer is yes, because if we take the curl of the field, so we're going to take the curl of A prime, That's going to be the curl of A plus the gradient of psi. Okay, and that's going to be the curl of A plus the gradient of the curl of the gradient of psi, and this thing is 0. That's a vector identity. So the answer is yes, we are allowed to change A by adding a gradient of psi. We can do that. Now, why would we want to do that? Well, there's a very specific reason. So, for instance, if we have the divergence of A, and we do the divergence of A prime, then that divergence of A prime is the divergence of A plus the Laplacian of that psi, which means that we can make this divergence look like anything, and we have complete freedom in picking that. So rather than picking picking psi, we pick the divergence of A. And that's our gauge freedom. That we can take the divergence of A and we can make it look like anything, as long as it follows this rule that it needs to look like something that is the Laplacian of psi. But we can formulate that. We can formulate that in terms of the divergence. Okay, so if that's the case, then we can actually go back and we can go back. So now we can go back to Ampere's law. So in differential form, so Ampere's law, curl of B is 4 pi over Cj. And now we can insert here the curl of B, we can insert the curl of A. And we know that the curl of A is minus the Laplacian of A. That's a vector identity. We've used this a couple of times before. And this is the gradient of the divergence of A. So this is a vector identity. For double derivative. I'm not sure if you call that a vector identity, but this is always true. This is not something specific to A. And now here we have our gauge freedom. So we can pick this to look like anything. So why not take the most easy solution? So pick. So we're going to pick the divergence of A as 0, and this is known as the Coulomb gauge. Oops. In that case, we go back to our equation. That means this becomes 0. Oops. This becomes 0, and now we have minus the Laplacian of A is equal to 4 pi over c j, or minus plus. And this is now what is basically the Poisson equation for A. And compare to to 4 pi rho in in electrostatics. So you see it has the exact same formulation. And again, that is not a coincidence. We can do this because phi and A actually are two parts of a 4 vector. And now you can also already see that rho and J will also be intimately related once we throw relativity in the mix. Now, how real is the vector potential? For a really long time, physicists were, they were aware of the fact that vector potential was a useful concept, but it wasn't necessarily considered to be a more physically realistic description than just do everything in magnetic fields. Now, turns out that there's a really big exception to that. So I need to walk you through how that works. So let's say we consider some kind of a line integral through a vector potential field. And we can, with Stokes, we can write that always as the curl of A integrated over that surface area. And the curl of A is, as you know, B, right? So that's B ds. And that is, oh, I'm running out of space. Is BDS. And that is the magnetic flux. So phi sub B, that's how I sometimes write it. So that's interesting. So you can take the line integral through A, some kind of a vector potential, and it's going to be equal to the magnetic flux that is poking a hole in that surface. So let's talk about a real situation where you would see something like this. So let's say we have some kind of a let's take some kind of a contour. So we are going to integrate over this contour, and we're going to call this the contour C. And I'm going to make it blue. Okay, so we're integrating, and that's our contour C. So according to this very straightforward little calculation, basically the closed vector potential integral, line integral of the vector potential over some closed contour is going to be equal to whatever flux is threading this surface. And notice that this is not the same as Faraday's law. So let me say NB, not Faraday's law, where we do a EDL is minus ddt of phi b, right? So there's an extra derivative, but it might look similar because that EDL is also a closed line integral. Sorry, also closed line integral, and then there's a phi b on the right hand side. So we're not talking about Faraday's law, we're talking about something physically distinct. Okay, so what can we do here with a magnetic field? Well, so for instance, we could make a magnetic field here that is nicely confined here. So making all these magnetic field lines, but we're going to make sure that these field lines are confined to a region smaller than C. Okay, how can we do that? Well, we know now that, for instance, we can do this with a solenoid. Remember that we had a solenoid where we took a solenoid like this, and we had a current that was flowing like this. And then the field inside was non-zero. B was non-zero, but field here, B is 0. So what does that mean? As even if the solenoid's not infinitely large, if we're close enough to that solenoid, we are definitely in a region where the B field is 0, but the vector potential is not. Okay, so what does that mean? Well, the vector potential integrated over that contour C is going to be, where was I? So this is going to be A times 2 pi r. And our phi b is whatever that field is. So A is our magnetic flux over 2 pi r. And therefore, even though we have a flux and we have no magnetic field, we do have a vector potential. And that vector potential is definitely non-zero as long as we're, r has not gone to infinity. So so it turns out that this is actually really important in the Aharanov-Bohm effect. So Aharanov-Bohm effect. So in the Aharanov-Bohm effect, you take a beam of charged particles, for instance, or doesn't need to even be charged particles, but it works really well with charged particles. And you make them go and choose 2 different paths. And we have some magnetic flux here, but we make sure that that flux is confined to a region such that the path where these charged particles or these particles are moving, the magnetic field is 0. So we're going to make sure that B absolutely is 0, but A is most definitely not 0. Then it turns out that for particles that go over a path like this, they pick up a quantum mechanical phase difference that's equal to Q over H bar. I'm running out of space. Hang on a second. So they pick up some kind of a phase difference that is Q over H bar A dl. And hopefully you know that if you change the phase difference from one path, between one path and another path, you can change the interference here from constructive to destructive. So in other words, what you can do is you can look at the detector here, and as a function of the magnetic field, you will go from constructive to destructive interference just by virtue of this vector potential, even though the magnetic potential, magnetic field is 0. So quantum mechanically, it turns out that the relevant field is actually not B, it's actually the vector potential. So this is not a intellectual exercise. It is real. All right. Well, ladies and gentlemen, that was the end of this chapter. Where are we? Chapter 4. So we're making good progress. Hopefully we'll be able to make it through. You've probably seen that I've skipped a bunch of things. There's quite a long discussion about what kind of prefactor sits in front of the delta function when you describe the magnetic potential. That's an important discussion, but we have to draw the line somewhere, so we're going to skip over that. So that means we will go into induced electromagnetic field. So therefore, Ampere-Maxwell's laws, and then we're almost done with the basics, and then we'll get to the really exciting stuff.